think I left myself a whole blank page. I did. Great. So continuing along. So I'll remind you from our spherical harmonics that the Legendrin squared times the YL/ML of theta phi. So all of that equals negative L times L plus 1 times YL/ML theta phi. So basically my Legendrin square operator, right? If you notice the way this is going, the Legendrin operator operates on the angular wave function, and I get back an eigenvalue and the original wave function. Okay, great. So we've already solved that. We did that in the other section. And I'll also remind you, right, when I look at like a term like this, let's say, so let's focus on this term, y has only dependent on theta and phi, whereas r is dependent only on r. So that means in this term, for example, my y term, I can take out in front because I don't have to worry about taking the derivative of y with respect to r because y is only dependent on theta and phi. And I'm going to do the same thing when I inspect through these other equations. So for example, right here, we can see r and y. We now know that Legendrin squared is only dependent on theta and phi. So also this big R right here, I'm going to be able to take that out in front as well. Okay. So when we do all of that, and I don't want to rewrite that big cumbersome equation, so I'm going to focus now on rewriting this big equation at the bottom and taking out all of those dependencies. So let's focus on this first term. Okay, that first term is going to become big Y, and so right, my big Y here equals my YL/ML of theta and phi. I'm just only writing Y to make it a little bit easier to write. Okay. So that becomes Y divided by R times the second derivative in R times R times R. All right. And now we can see already, if I go back and now focus on this term, 1 over R squared, Legendrin squared times R times Y. Well, I know I can take that R out. Okay. And when the Legendrin operates on y, just as I showed you, we get negative L times L plus 1 and the original wave function y. Okay. So now that second term becomes negative L times L plus 1 divided by R squared. And then I can substitute back that R. It doesn't matter what order it's in. And then times y. Okay. And then now I've got my potential energy term that I'm going to write, okay? And so now that's plus ZE squared mu divided by 2 pi epsilon R h bar squared, and that's still times RY, because this is just a bunch of constants, so there's no operation there. And then now that all equals my K solution, which I know K is negative 2me over h bar squared, right? M, remember, me and reduced mass. They're interchangeable for my electron-proton system. And that's still times ry. Okay. So now what I can do, you notice that I've got a y in each of these terms, and there's no operations that I've got to carry out on y that would prevent me from canceling it out, right? I don't have any more derivatives or operations I have to do on y besides just multiplying, and that allows me to cancel it out. So I can reduce y from each one of those terms, okay? And I can't quite do the same thing for r because I have this pesky little derivative term, okay? So there's a little trick that standard quantum mechanics books do, and that is they call they make a new function, u of r equal to r times r of r. And so I'll just remind you my nomenclature up here, right? Where I've written capital R, that's really my radial component of the wave function, okay? So this is standard manipulation in quantum mechanics. And the reason for that is because it makes our life a little bit easier, as we shall see. Okay, so I'm just studying my notes here so I can carefully transition those. All right, and oh, and then I did one last algebra that I forgot to do, and let's do that. So we eliminated y, and then because we've got this 1 over r here, we're going to multiply both sides of the equation by r. Okay, so when I do that, let's see here, what happens? Let's see. Oh, yes, when I do that, so I'm going to say multiply by r, and that cancels that r and that r. And then now I'm going to say multiply by r, and that's going to give me that r function. Also, because I'm multiplying everything through by r, I have to do that one as well. Okay, and then I have to do this one as well. And again, this is not something I'd expect you to just say, oh, multiply everything by r, and then come up with this new function u of r. This is standard manipulation because it's going to make the differential equations easier to solve. And so now when I rewrite this equation, let me just see what I have next. Yeah, okay. When I rewrite this equation now, I've got partial of r squared, and then r is my u of r function, okay? And then now that's going to be minus L times L plus 1 over r squared times u of r. And remember, we've eliminated y. And now that's going to be plus z e squared mu over 2 pi epsilon r h bar squared. And once again, r times r gives me this new function u of r. And all of that equals negative 2 mu e over h bar squared times u of r. Okay, brilliant. So now I'm going to go to the next slide where I've got this equation written. And what I want to do is collect like terms. And I'm going to collect like terms for the kinetic energy and for the potential energy. Okay? So when I go to this next slide, it's the same equation here, but we've just rearranged it so that we can talk about this equation in a meaningful way.